All right, so let's review for a second, then we're going to put it in there. So does everybody understand that delta y is going to be the change in the y values on the actual blue curve? So that's x sub 2 minus x sub 1. Then dx is going to be the change in the x values on this red tangent line, which again is going to be x sub 2 minus x sub 1. So delta x and dx are exactly the same number. But now look at delta y and dy. Delta y is the change in the y values on the curve. So from this point to this point is a vertical distance, a vertical difference of this point right here, delta y. Is everybody okay? Now dy, though, is not going to be the same thing. From here to here is going to be dy. Julia?
Is this why we take derivative with respect to x, or do we take derivatives with respect to x because of them?
Say that again, I'm sorry.
If delta x is equal to dx,
Right.
is that why we take the derivative with respect to x, or is that because we take derivative with respect to x?
I'll have to think about it.
Like the fact
I
that
think it's because we take the derivative with respect to x, but I'll think about it and get back to you. Okay, now, but you see the difference? This delta y and this dy are what? They're not the same. But look what happens. If you move this curve, if you move this point down this curve, what's going to happen to delta y and dy when this point is really close to this point? What is true about those two values? They start getting what? Closer. So what happens is with certain conditions, delta y is approximately equal to the change in y. Now, with dx and delta x, they are exactly the same. They are interchangeable. But with dy and delta y, they're not the same. But this is going to be true when delta x is small. In other words, I can't move over very far. If I move over a big distance, these distances are going to get further and further and further apart. Is everybody with me? But when my change in x is small, delta y and dy are approximately the same thing. Now, why is that helpful? We're going to see in a second. Because sometimes this value is quicker and easier to find than this value. And in the real world, sometimes close is good enough. Okay? So we're going to do a couple with these two things. Now, let me make sure we're clear about something. How would you find your actual change in y on your curve? Wouldn't it be kind of y sub 2 minus y sub 1? Is everybody with me? Correct? Now, let's go back to a second. I'm going to change, instead of putting x2, y2, I'm going to change it a little bit. Instead of putting x2, couldn't I say f of x plus delta x? So I could put x plus delta x and then f of x plus delta x. In other words, if I'm going to move over delta x, instead of putting x2 and y2, isn't that how I would find x2? I'd take my x1 and add a little bit, and then I'd plug that number into my function. So that means that I would have f of x plus delta x, that'd be really what y2 was, minus f of x. So again, instead of calling this x1, y1, I could call it x, f of x. So that's your formula for delta y. So let's go look at something real quick. What they're going to want you to do at first is actually find some things. Now, I'm going to write this formula down so we don't forget it. All right. So the change in y is going to be your second y value minus your first y value. Okay. Now, they give you a definition on page 272 of dy. This dy is called the differential. And it's f prime of x dx. Now, so notice what happens. Suppose f of x is something simple like y equals x squared, that parabola. All right. So suppose I tell you something like this. Let's see how they're going to word it on yours. If x is 3 and delta x is like 100, find delta y and the differential of y. So these are your formulas. There's your formula for delta y, and there's your formula for the differential of y. So we're going to find both and then compare the two. Look at delta y. F of x plus delta x minus f of x. So in this problem, what's our x value? 3. Plus, how far are we moving over? What's our change in x going to be? Isn't it 100? Everybody okay? Minus f of, now what's my x value? It's what? 3. So does everybody understand what we're saying? Now I'm going to enlarge it for sake of argument. So you have y equals x squared. So we've got some point here when x is 3, and now we're moving over to 3.01. Is everybody with me? And we're trying to figure out how far that thing's actually increased. Well, that'd be f at, let's go back to that same color. Now, what does f at 3 and 100 want you to do? Take 3 and 100 and plug it in your what? In your function. All right, there's your function. So you got a calculator, take 3 and 100 and plug it in there. All right, what'd you get? 9 point what?
601.
601? 0601? All right. Now, just take 3 and plug it in there. When you take 3 and plug it in there, you just get 9. So the difference is decimal 0601, 601 thousandths. Do we agree? That's our actual change in y on the curve. Now instead, let's do the change in y on the tangent line. What's the differential of y going to be? Well, by definition, it's f prime of x dx. So I'm going to need to find the derivative. All right, what is the derivative of my function? 3x squared, isn't it? So 3x squared dx. I'm sorry, 2x. Benadryl's a bad thing. All right. Now, what's my x value going to be? 3. Now, they didn't give me dx. How do I know what dx is? It's the same thing as what? Delta x. We said dx and delta x were identical. They're interchangeable. So if delta x is 100, dx is going to be what? 100. So what does that answer come out to be? Point what?
26.
Are they exactly the same? No, but are they close?
Yeah.
And without a calculator especially, that one's way easier to compute what? Than that one is. Okay? So in the real world, sometimes when they actually need delta y, they'll go do dy as an approximation. So one thing you have to do in your test is that I might give you a function and an x and a delta x and tell you to find me the actual change in y and tell me to find the differential of y to show me that they are close. Now, what would happen if you did this just to show? What if instead your delta x was 5? Go recalculate them. All right? So x is 3 and delta x is 5. Go find me delta y and dy. All right, this time you've got a 3 plus a 5 minus f of what? 3. So you got f of 8 minus f of 3. So what's f of 8 going to get you? 64. What's f of 3 going to get you? 9. What's that difference going to be? 50 what? Everybody okay? Now over here, when you put in your 3 and you multiply by 5, what does that come out to be? Are those remotely close? No. Why are they not close? Because that delta x is huge. When are they going to be close? When delta x is what? Small. All right? So what you don't want to do in the real world is use something for an approximation when it's not a good approximation. So the only time that delta y and dy are good approximations of each other is when the change is small. Then they're pretty interchangeable. So, question.
So what would you, like, in real life have to do other than just like make it obviously closer to?
I mean, how could you make them a better approximation of each other? Some of that will vary with the formula. I mean, some formulas you have more wiggle room than others. They don't, when you start squaring something, it gets big pretty fast. If you're multiplying something by half, not so much. So some formulas, so to speak, are friendlier and they'll take more error. But generally speaking, you really don't, you want to have a decimal number probably there. Okay. Now, one of the things they do in your book is they show you a real life example of what they're doing. And basically it's things like, if you got a ball bearing in a machine, as that machine spins, what's going to happen to that metal ball over time? Or do we know? Well, let me ask you this. You go to the drink machine out here, right? You put a quarter in, the quarter falls out. You pick the quarter up and you put a quarter in, you stand on one leg and it still falls down. You see what I'm saying? You hold your breath and it still falls down. You get another quarter out of your pocket and it likes that quarter. Why is it like the second quarter but then like the first quarter? It fits. When we say it fits, what do we mean? What happens over time to money, metal, whether it's in a ball bearing in a machine or money in a machine? It starts wearing down. All right. So what happens is those machines are calibrated. All right. In other words, when the mint, when the national mint makes money, every quarter doesn't come out exactly the same size and weight. It's got wiggle room. Okay, any kind of measurement is going to be approximate. There's no such thing as an exact measurement. That's an oxymoron. Okay, you can't have an exact measurement. So you got wiggle room. So what happens over time, those machines are calibrated pretty close though, because it doesn't want it taking like a bet or some false thing is money. So over time, that metal just wears away. So old quarters or even younger quarters, newer quarters that have been used a lot in circulation, they're worn down. The machine doesn't recognize it as a quarter. It's either off on weight or it's off on size. Okay, so the same thing happens with the ball bearing. If you got a machine where that ball, something spins around that ball, that metal is wearing down over time. So again, in things like production, the amount of error and wiggle room between, say, the real volume of the ball and the approximate volume of the balls is pretty important. And sometimes this is just quicker and easier to calibrate. Now, for test purposes, you're going to do two things for me. Then I'm going to show you one thing it used to be useful for, but not so much. I'm going to give you a function and an x and a delta x and tell you to find me delta y and dy. Is everybody cool with that? All right, the other thing I may ask you is to find me a differential. So a differential is just f prime of x what? Dx. This is your general differential, just like you have general derivatives. And we're going to use them for some things in Calc 2. Okay. So if I give you something like this on a test, and I say find dy. Okay, I didn't say find dy to dx. I didn't say find the derivative. I said find the differential. Well, what's your formula for the differential? It's what? F prime of x what? Dx. It's not f prime of x. It's f prime of x times what? Dx. So I would expect you to write down, now what is the derivative of this thing? 18x squared what? Minus 4. But you better have that dx on it. That's your general differential. In other words, that's a formula, so to speak, an equation that will give you the actual differential in any x and dx that you want. Just like you can have a general derivative, or I can tell you to find the derivative at 4. Is everybody with me? So one's a particular value, one's the general equation that gives you any particular value. So make sure that if I ask you to find the differential, you don't forget that dx there. Now, naturally, if these were z's, that'd be a d what? But that's the two things on your final that you're going to have to do with the differentials. Are we okay? Now, let me show you something that this used to be pretty useful for, but not so much now, because those calculators exist. What if you were doing a calculation and you did the square root of 16 and 5/10 approximately? And you don't have a calculator. Well, my understanding is this is one of the very useful things it would do. In other words, I really want delta y, but I'm going to use dy. Now, what's my function going to be? My function is the square root of some number. Is everybody with me? Now, how do I know what my x and my dx are? Well, I need to think of a perfect square that's close to this number. So what's the perfect square that I know that's close to 16 and 5/10? Square root of what? 16. Is everybody with me? Now, what's the change in this? This isn't the square root of 16. So what am I moving over by, so to speak? 0.5. Is everybody okay? So what I'm really wanting to know is, I need to know, I can do a substitution there sort of to figure it out. Is everybody with me? All right, so basically what I've got to know is this. I need to know what my f of x plus kind of delta x is. All right, so if I can use 4 6/10 and play with it. Now, they've got one work for you on the bottom, page 275, which is the one that they've got now. Now, they've got this one worked out in your book. Page, what was it? 275. Okay.